Okay, so today we're talking about cycloalkanes. We're going to do nomenclature of cycloalkanes today, and then on Friday we'll do enrichment on both isomers and cycloalkanes. So we're kind of do enrichment for the whole week on Friday. We're going to do cycloalkanes today so that you have all the information you need in order to do your homework. After today, you should be able to do it. Cycloalkane nomenclature is not very difficult, so I don't think it's going to be a challenge. But nonetheless, let's spend some time talking about it. So when you take the linear version and you loop it around with itself, right, make a bond between here and here, you have to lose one of those hydrogens, right, and you have to lose one of those hydrogens, because if this is CH3 and this is CH3, and we make a bond here and here, well, obviously we can't have a carbon with that many bonds. So it has two fewer hydrogens than the linear version, right? If hexane is C6H14, cyclohexane will be C6H12, because each one of these is going to have two hydrogens on it, right? You can't have a carbon with three hydrogens on it. That wouldn't make sense. That violate what we know about how many bonds a carbon needs. And so this is a figure from a textbook, right? They're showing the ball and stick for 3 carbon, 4 carbon, 5 carbon, 6 carbon chain, right? There's what it looks like in a condensed molecular. And then if you're drawing it in skeleton notation, right? And then the names. So we use the cyclo prefix when we say that something is in a ring, right? So this would be cyclohexane, this would be cyclopentane, cyclopropane, etc. And when we name using IUPAC rules, obviously we add cyclo to the parent chain. So if it's a hexane, it's now a cyclohexane. And just like we did when we named alkanes, we're going to put our substituents in alphabetical order, right? So ethyl comes before methyl. If you've got multiple substituents, we're going to use the lowest set of numbers. And what I mean by that is there are, since this is in a ring, you can number clockwise or you can number counterclockwise. So let's pretend that we've got a cyclohexane and we've got, let's just call this X and Y, all right? X comes before Y, right? So this would be carbon 1. Now, we can number clockwise and be 1, 2, blah, 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 right? Or we can number counterclockwise and be 1, 6, blah, 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 blah. Which one is correct?
1, 2.
The 1, 2, right? You want a number so that you use the lowest possible set. So that means that when you've established who's carbon number 1, now you need to decide, do I number clockwise or counterclockwise, right? And the way we do that is the way that gives us the lowest set of numbers. 1, 2 is correct, 1, 6 would be incorrect. And then if there's a single substituent, then you don't need a number. So if it's just, let's say, a cyclopentane with a BR, right? That by definition is carbon number 1. You don't need to say 1-bromo because there's only one substituent. So by definition, it's on carbon number 1 because this is a ring. Okay. Now, if this were a pentane 1, 2, 3, 4, 5, and there was a bromine, yes, you would need to say where it is because that bromine could be on number 1 or number 2, right? Or number 3. So you do need it for the linear, you would not need it for the cyclic. So a little bit different, but essentially the same pattern. Like I said last week's lecture was the worst. I made it through last week. Now it's just basically variations on the theme from here on out. So that's the good news. So here's an example. This is a 6 carbon chain. This is drawn using Lewis structures, which I hate. I think that's awful. But, you know, textbook gives us some options, so I like to throw out all my options. There's a chlorine here. So this is carbon number 1. There are no other substituents. And this is a cyclohexane, so it's just chlorocyclohexane, right? You don't need the 1. If you put it there, it's redundant, right? That's like saying Dr. So-and-so, comma, MD, right? Because they both designate having a doctor. So it's either one or the other, or both. So for this one, let's do it together. The substituent is a what? Which is called a what group? A methyl group, right? And how many carbons are in the chain? 1, 2, 3, 4, 5. So this is a cyclo. Right, so this would be methyl cyclopentane. You don't need a 1 because there's only one substituent, right? All right, now when there's more than one substituent, again, carbon number 1 is the substituent that comes first alphabetically, and then we want to number the correct way so that we pick the lowest numbers. So here's an example. Here's the correct name. 1-ethyl, 3-methyl cyclohexane, right? 1, 3. E comes before M. That's why this is carbon 1 and this is carbon 3, right? E comes before M. We numbered counterclockwise. Why is it not 1-methyl, 3-ethyl? How come this is not carbon number 1? Right, ethyl comes before methyl, so that's why this cannot be carbon number 1. And then why is it not 1, 5? Right, we want the lowest numbers, so that's why it's not 1, 5. Okay, so you take a second and try this one. 1-ethyl, 2-propyl cyclobutane. Okay, let's go over this one. If you had the same thing, counts like a frog, right? If you had the same thing, if you had this swapped with this, right? You had the 3-carbon chain here and the 2-carbon chain here, would that be different? It's the same molecule, it's split, right? Okay, now name these two. I'll pause the video, give you a chance to try those. Zoom. Okay, for the top one, does it matter which I pick for number 1 between this one or this one? This one could be number 1 or this one could be number 1. You're still going to be 1, 2, 3 or 1, 2, 3 either way. But don't forget, you need that tri, right? It's not 1, 2, 3 methyl. It would be 1, 2, 3 trimethyl, right? Because you need to tell the reader that carbons 1, 2, and 3 all have methyl groups. And then don't forget the cyclo. That's another common mistake I see. Students will say 1, 2, 3 trimethyl pentane, right? That's not the same thing as 1, 2, 3 trimethyl cyclopentane. It's going to be something very different. Okay, for the second one, we need to pick carbon number 1. Is it going to be the one with the bromine, the chlorine, or the ethyl group? Right, the bromine. And then we're going to number. We need to decide how we're going to number. Counterclockwise or clockwise. We're numbering clockwise, right? 1 bromo, 3 chloro, 5 ethyl cycloheptane. It's a 7-carbon chain in a ring. We good on these two? Okay, let's talk about conformations again. Remember what conformations are, right? That's the like standing on 1 foot versus standing on 2 feet, right? One's more stable than the other, but we don't have to actually break bonds to go from one conformation to another. Now, when we had a linear chain, there was full rotation, right? I could rotate that bond as much as I want, the full 360 degrees. But when we have a cyclic, you don't have that full rotation 360 degrees. You can't, because the bonds can really just shift a little bit. They can just kind of shift angles a little bit. So there are 2 conformations that we're going to talk about in elementary organic. When you take full organic, you'll talk about more conformations, but these are the 2 that we're going to talk about in elementary organic. So we're just going to look at cyclohexane. Okay, we're just going to look at cyclohexane. There's what it looks like as a Lewis structure. There's its skeleton. Okay, now remember, this is a tetrahedral carbon. So we can just kind of wiggle a little bit, right? We can't do full rotation now that we've got a bond on each side. So this is what I just said. There are 2 conformations of cyclohexane. One of them is called the chair. So if you're taking this and you're looking at a model of it, and you're looking at it from the side. Okay, so imagine you take this and you rotate it up so that you're looking at it from the side. And that's what we're doing. This one is called the chair. So every other CH2 is up. In other words, up, down, up, down, up, down. You see how that looks from the side? Kind of looks like a chair, right? And E stands for equatorial, and A stands for axial, right? Axial sticks up. Equatorial is on the side, like the equator. Okay, this one is more stable. It's called steric hindrance. There's less of that in the chair. Here's the other conformation. It's called the boat. Can you see why this one would be less stable? Because look what happens here, especially if you start getting bulky substituents here, right? These two are going to be in each other's face. They're going to be crashing into each other. So the boat is less stable because of that space at the top. Right, so there's the chair again. You've got more space between everybody. And there's the boat. And we're going to make models next week. Again, we're only doing conformations for cyclohexane in elementary organic. When you take full organic, you will apply this conformation theory to all kinds of cyclic molecules. But this is elementary organic. We just want to introduce the idea, okay, so that when you take full organic, you've seen it. So this is what conformations look like in cyclohexane. Only a 6-membered ring we're going to be looking at in elementary organic. And then there's a link if you go to the website and download the notes. That's a link that you can go to and you can rotate it and see it in 360. Now we also have isomers in cycloalkanes. Again, if you have that ring, right, the way we draw a skeleton, you're looking at it from the top. But let's pretend that you've got that skeleton and you're looking at it from the side. Okay, so if this is the ring, you're rotating it up and you're looking at it from the side. Okay, you notice that you could have a position where, you could have a configuration where one methyl group's up, one methyl group's down, right? Or you could have both methyl groups down. So in other words, this one will be coming out of the board toward you. This one will be behind the board, right? Or behind the screen, I should say. Whereas in this version, they're both behind the screen. Do you see how that would work? This is the top. These are behind the screen. This one's behind. This one's coming out. And those are different. And so we use the dashes and the wedges to show isomerism. So if I say to draw the isomer, you have to use these dashes and wedges. Right? This one's in front, this one's behind, whereas here they're both behind. And so cis, the cis isomer, has the same face, right? So they're either both behind or they're both out. So if I said draw cis 1,2-dimethyl, blah, 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 right? You would need to use those dashes and either make them both dashes or both wedges. I really don't care. In the other option, the trans, you've got one coming out and one going behind. Okay, so if you're going to draw a skeleton notation and you're going to show cis and trans, you've got to use wedges and dashes. Because if you just draw a stick, right, a straight up stick is looking at it from the top. If you're drawing a stick, you're looking at it from the top. And the one we looked at here is looking at it from the side. Okay, that's why we could get away with drawing a stick here, because we're looking at it from the side. But if we're looking at it from the top, right, that's why we've got to use the dashes. And if it's cis, they're both the same. So either both behind or both forward. And if they're trans, one and one, right? They're opposite each other. Now, if I don't say cis or trans, if I don't say draw cis trans, then you don't have to worry about it. Likewise, if I don't give you wedges and dashes, then you don't have to worry about it. Okay? In elementary organic, we're going to keep it simple. Do you understand how this works? We're going to do some practice with it too. Right? So how would we name this? If I gave it to you like this, if I gave it to you using dashes and wedges, I would expect your name to include cis or trans. Okay? So this would be trans 1,2-dimethyl cyclopentane, and this would be cis 1,2-dimethyl cyclopentane. Could these two be distinguished from each other in the lab, different boiling points? Yeah, they could. They would have slightly different intermolecular forces. Because remember, isomers are the same molecule, just put together differently. Right? They have the same formula put together differently, I should say. So they are going to have different physical properties. Now, if I give you this, I didn't specify cis or trans, right? So the name of that would just be 1,2-dimethyl cyclopentane, right? Because there's no wedges and dashes. I didn't give it to you that way. Right? So there's trans, looking at it from the side, right? What we're doing when we draw the skeleton is we're looking at it from the top. But when we see it from the side, there's clearly trans, right? One's up, one's down. And then there's cis. Again, looking at it from the top versus looking at it from the side, they're both the same way. All right, so let's do a few practice problems. So I'll pause the video and give you a chance to draw these. Let's go over this one. 1,2-dibromocyclobutane. Did I say cis or trans? Nope, I didn't specify, so you don't need to use wedges and dashes here. Now here I did say cis. So cis means same or different. Same, right? So they're either all three going to be wedges or all three going to be dashes. You pick. Right, so there's what that would look like. 1,3,5-trimethyl cyclohexane. You just make the whole methyl group, right? If normally you were drawing a methyl group, you just draw it as a stick. Well, now you're drawing a wedge. What if this were an ethyl group? Just for practice. What if the name of this were 1,3,5-triethyl? You would draw it like that. That's how you add the second. So it's only a dash or a wedge at the point of attachment. And if it were propyl, right, it would be that. My angles are getting funky, but who cares? Okay, you see how that works? You only need to draw the dash or the wedge at the attachment point. Oops. Okay, I'm actually going to skip this because it's on the next page. So let's do this last one. Name this guy or gal. We don't want to give sexes to our molecules. Okay, name here. Is this going to be cis or trans? This one's trans, right? It'd be trans 1-ethyl-3-methyl, right? Why is it this is number 1 and not this? Because E comes before M, and then we rotate, or going clockwise, excuse me, we're going clockwise or counterclockwise, we're going clockwise. And then last one, give me this molecule, 1-bromo-2-chloro, cyclopentane. Let's see what we got. Bromo, chloro are my substituents. If you had, let's just pretend you had the bromo here and the Cl here. Is that wrong? If you had Br here and Cl here, would that be different? Nope, it's just the same molecule rotated. Okay. So long as your orientation between the substituents is the same as mine, then you're fine. Okay, so what we're gonna do now is I've got a file that I'm going to give you. Read only. Okay. I'm going to do this in the screen share version. Okay. So I'm going to put these problems up. So if you're taking this as, if you're watching this as an online student, you can try these on your own. Here are some problems that on-campus students are going to do, and I'm going to pause the recording, let everybody try. All right, we're going to do these here in class. Name these molecules. There are problems for number 1, and then draw these. Okay, there's the problems for number 2. And then for number 3, look at these 2 and decide, are they the same molecule, are they unrelated molecules, or are they isomers? And then explain. So if you're watching this video online, pause the recording, try it on your own, and then hit resume when you're ready. If you are an online student, you can also download this file from the course website. Try it on your own and then watch the video when you're ready. For those of us on campus, I'm just going to pause the recording while we work on it, and then I will resume the recording once everybody has had a chance. So pause. Okay, let's go over these. Again, if you were doing this online, you can try these on your own and then pause the video and then resume when you're ready to see the answer. So for the first several, we're just naming. This has no substituents, right? My kids would call it a stop sign. What is it? It's just cyclooctane, right? Cyclooctane. And yes, there are two O's back to back. It does feel weird doing, but that is the name. All right, B. How many carbons are in this chain or in this ring? 1, 2, 3, 4, 5, 6, 7. That's a 7-membered ring. So what's that called? Right, that's just cycloheptane. And what's this? Cyclopropane, right? I think I could slide the up enough and see those ones on the bottom. Yeah, we can do that. And then D is cyclobutane. Okay, for E, this has no substituents as well, so it's cyclopentane. And F would be, right, methyl cyclopentane. Is the 1 in front of it necessary? No, that's unnecessary information. Okay, in G, we need to decide who's carbon number 1. This is a methyl group. What's this? 1, 2, 3. That's a propyl group. So who comes first? Right. And then are we going to number clockwise or counterclockwise? Okay, so we're going to go 1, 2. That seam is in a really lousy spot. All right, so this would be 1 methyl, then what? 3 propyl, cyclohexane. And for H, we've got a what group? A methyl and an ethyl. Now these are this is drawn using dashes and wedges. So what do we need to include in the name here? Right, trans. Because they are different from each other, that means that they are on opposite sides of the plane. So this is trans. Now we just need to decide who's carbon number 1. This one or this one? The one with the methyl or the one with the ethyl? Okay. And are we numbering clockwise or counterclockwise? Counterclockwise, right. Because if we number clockwise, it'd be 1, 2, 3, 4, 5. It'd be 1, 5 versus 1, 2. So this is trans, 1 ethyl, 2 methyl, and don't forget that cyclo what? Pentane. Very common to forget the cyclo part. Very common to forget the trans part. Those are the 2 most common mistakes I see with those. All right, let's go on to problem number 2. Alrighty, number 2. We're gonna do some drawing. Let's see if this marker writes a little bit better. That one's in a little bit better shape. Okay, so we're drawing a cyclobutane, so that's a 4-membered ring. 1 ethyl, 1, 2, 2 propyl, 1, 2, 3. We actually did that one in the slides, right? I gave it for you to do in the slide. Okay, pentane is a 5-membered ring. 1, 2, 3, 4, 5. Don't forget to link it back up. 1 bromo, 2 chloro. Do we agree? If you had, is that different? Same molecule, right? As long as your spacing is the same. I think both of those were actually in the practice problems in the notes. Okay, this is a cyclopentane, so this is 5, and it's trans. So what does that mean? There's both dashes and wedges, right? So let's just pick arbitrarily what we want to do, dashes and what we want to do wedges. 1 ethyl, let's do that. And then 2,4-dimethyl, 2, 3, 4. Let's do that. If you had made yours different, but the spacing's the same and they're still trans, then I'm happy. Okay? Because technically we've got 3 substituents. We're not gonna get all obsessive and intra-organic. Okay. And then cyclopentane again. 1, 2, 3, 4, 5. Don't forget to close the ring. This is cis, so what does that mean? Same. So we've got 1-ethyl. Let's just do this one dashed. And then 2,4-dimethyl. Again, it's the same molecule, right? Just different isomer. So what's the relationship between these two? Are they the same molecule, unrelated, or structural isomers? These would be structural isomers, right? Would they have different boiling points? Yes, they would. These are going to have different intermolecular forces. The cis-trans is going to make them stack on top of each other differently. They're both only going to have London forces, but they will have different degrees of London forces. So yes, they will have different boiling points because they have different London forces. Okay, and then for the last one, I gave you 2 molecules and asked you to decide what their relationship was. Same molecule, unrelated molecules, or isomers. And by isomer, I mean structural isomer, because we're not worrying about stereoisomers right now. What's the relationship between these two? Well, let's first make sure they're the same formula. Right? This is a cyclopentane with a methyl group and an ethyl group. This is a cyclopentane with a methyl group and an ethyl group. So do they have the same formula? Yeah, they're going to have the same formula. Are they going to have the same name? No, they're not. All right, this one is going to be 1-ethyl, 1-ethyl, 3-methyl, cyclopentane. And what's this one?
1-ethyl, 2-methyl.
Right, 1-ethyl, 2-methyl, cyclopentane. So what's the relationship here?
Are they isomers?
Yep, they'd be structural isomers. They would have different boiling points. They would be able to be separated in the lab. If you had a mixture of these two, you could separate them. Okay, for B, same molecule, different, like as in unrelated, or structural isomers? They're the same, right? This is the same molecule. Right, because what's the name of this? This is trans 1,2-dimethyl cyclohexane. And what's the name of this? Trans 1,2-dimethyl cyclohexane. They're the same molecule. So same molecule. You couldn't separate those in lab because they're the same thing, right? Just like you can't separate you from yourself. It doesn't make sense. Questions on these before we stop? Okay, well that's where we're going to end for today.